I'm Jiang, a PhD student in Polytechnique in Paris. And today I present high-dimensional model selection with missing values in collaboration with Professor Gosia Bogdan and Blazej Miaso-Zhedov, who both work in Poland. And also my supervisor, Julie Ross, who has given a nice talk yesterday about missing values. So our project of missing values is motivated by an application in public health on severely traumatized patients. We have a medical data set with more than 20,000 patients and 250 measurements. So this is a subset of the data sets. The variables can include accident type, age, sex, blood pressure, etc. The objective is to help the doctors to develop models to help them to make decisions. For example, based on the measurements of patients, we want to decide the level of platelet, which is an important blood component. From a statistical point of view, based on we aim at performing predictive models based on the predictor variables X and to explain the response Y. The simplest example is linear regression. However, we have a challenge here is that how to select relevant measurements with existence of missing values. As we can see here, there are lots of missing values in this data. So first, let's define the notation. We denote Y, a vector of response of less n, and X, a standardized design matrix of dimension n times P. This is a classical linear regression formula with a parameter regression coefficient beta, and also a vector for the noise epsilon with variance sigma. We also assume that we are in a high-dimensional setting with P large and even can be larger than n. In addition, beta is sparse with k non-zero elements, k non-zero coefficients, and the popular method to deal with this kind of model selection problem is called lasso, proposed by Tipshilani. With the L1 penalization, we can detect important variables with high probability, but it can include many false positives. To solve this problem, Professor Bogdan proposed a method slope, which stands for sorted L1 penalization, and it penalizes large coefficients more stringently with larger coefficients, penalization coefficients lambda for larger beta. In fact, the model selection problem can be viewed as a multiple tests for beta, each element of beta equals to 0 or not. And if we choose the penalty coefficients lambda equals to a sequence proposed by Benjamin and Honchenberg, which is a normal quantile related to a rate Q, then in our standardized setting, the FDR, that is the mean of the number of false rejections among the total number of rejections of beta equals to 0, can be controlled at level Q. So this is so-called false discovery rate control. However, the lambda BH sequence lambda for slope leading to FDR control are typically very large. So slope often returns an inconsistent estimation. How can we improve the estimation in slope? First, we consider to modelize in a Bayesian framework with a specific prior, slope prior, involving also the sorted L1 term. So the slope estimate of slope can be viewed as maximum a posterior with this prior. And here we propose an adaptive version of Bayesian slope with a specific prior involving a weighting matrix W. And here I will detail about all the elements that we use in this prior. So first, we viewed beta as a signal if beta is large enough, otherwise only noise remains. And Gamma can be viewed as signal indicator, and we modelize a gamma as Bernoulli distribution with parameter data, and data is a sparsity. In addition, C is the inverse of average signal magnitude. And finally, we construct a diagonal matrix W, whose diagonal element equals to C if the corresponding gamma equals to 1. Otherwise, it is 1 in the diagonal elements. So why do we introduce this weighting matrix W? So first, we can say that if corresponding gamma equals to 0, then the element in W equals to 1. That means the null variables are treated with regular slope penalty, as showed in the left plot. But when the gamma equals to 1, which stands for the true signal, then the corresponding element in W equals to C, which is smaller than 1. And then the corresponding sequence W times beta can be put at the end of sequence, so we give smaller penalty for the true predictors than the regular slope prior, as showed on the right plot. And for the red stands for our AB slope prior, which has large value, which has a large tail but smaller value around 0 compared to the slope. In addition to the model selection problem, we have to face the challenge of missing value. So to avoid the loss of information, we have to modelize missing value. It can be the design matrix X can be decomposed into two terms, one observed part X obs and another missing part X miss. We denote M as a pattern of missingness, where the element in M equals to 1 if the corresponding entry in X is observed, otherwise 0. One common assumption is missing at random missing mechanism. That means the distribution of missingness depends only on the observed part. So for example, people at older age don't want to tell us his income at larger probability. And in our missing value literature, we have also to assume a distribution for the covariates. Here we begin with a normal assumption with parameter mu and sigma. The problem is that with missing values, only a few methods are available to select a model, and their performances are limited. For example, Clarkson and Consino propose to adapt AIC for missing values, but it's impossible to deal with the high-dimensional analysis due to the computational difficulty of stepwise method. And Long and Wainwright propose to propose a lasso with missing values, but their method involves a non-convex optimization, and we also have to know the bounds of the L1 norm of beta, so it's difficult in practice. Now we summarize our model with a graphical model. Here there are variables in circle and also the parameters in square. With this graphical model, we can decompose our log complete likelihoods with different parts in the graphical model. But our objective is not to maximize the complete likelihood, but taking the missing data into consideration to maximize only the observed parts, and which integrates all the latent variables, including missing values, signal magnitude, and also sparsity and signal indicator. One common method to deal with this inference problem is to use EM algorithm, as Rudy has introduced yesterday. And a typical application is Monte-Carlo EM, which is expensive to generate a large number of samples. So here we propose to adapt stochastic approximation EM. The original E-steps involving the evaluation of expectation, conditional expectation with respect to the distribution of missing values, denoted by quantity Q. But here in stochastic approximation EM, we replace this state by drawing a sample of missing values from their conditional distribution by keep sampling, and then apply a stochastic approximation formula on the function Q with the complete likelihood integrating the sampled missing values. After that, in the end step, we estimate the parameters which maximize the quantity Q by proximal gradient descent, and also in the high-dimensional setting, we consider shrinkage of covariance estimation. So I won't detail much about our methodology, but we can find all the details about initialization, generating samples, and also the optimization part in our draft, which is available online. As we know, there is no package available in R to implement the model selection with missing values, so we have implemented our methodology in R package AB slope, which is available in GitHub now. So with their function create lambda BHQ, which provides a BH sequence aims at controlling false discovery rate, and our main function AB slope take the design matrix and response, also the lambda, and if we have some prior knowledge about sparsity, we can also put in this function AB slope as the parameter A and B. In addition, we have also implemented a fast and simplified algorithm using RCPP. And in this algorithm, we approximate AB slope by replace the generating missing values by a conditional expectation. So the output of our function contains estimation beta and also the signal indicator gamma, who can help us to do model selection. Now I present some results of simulation study. First is about the effect of parameterization. We simulate a dataset of n equals to p equals 100 without correlation and 10% missingness. We vary the number of relevant features, non-zero beta, and we also vary the signal strength from 1 to 4. And here we can observe that the false discovery rate can always controlled below the desired level, 0.1. And with larger sparsity and also with larger signal strength, we can have a larger value of power, and we can also reduce the prediction error. Here we consider the correlation matrix as a top-list matrix, which means the adjacent pairs in covariates are more correlated, while the covariables far away are less correlated. And here we see that if there is no correlation or small correlation, then FDR can be controlled. However, with a larger correlation, there will be a slightly loss of FDR control. And with the correlation, we can help the prediction accuracy, because in our methodology, we generate missing values depends on the observed parts. Now I will show you some result of model comparison. We consider non-convex lasso and also mean imputation followed by the slope with no sigma, also lasso and adaptive lasso, where the lambda is tuned by cross-validation, and we aim at control FDR at level 0.1. So here we vary the number of relevant features from 10 to 40, and also we vary the signal strength from 1 to 4. So in each method here, the left plot is power, and the right plot is FDR. Each method here, the darker color in each method means that the power is the value of power is larger, and here the lighter color indicates the FDR is smaller. And we see that almost every method can achieve a great power, but if we switch to the right plot, and we see that only our AB slope and the approximated version of AB slope can control the FDR below the level of 0.1. That means the other methods sacrifice FDR to achieve a good power. Also, our methodology has great advantage of the bias and prediction error. So now in terms of computational costs, we see that our AB slope, which is coded in RCPP, can accelerate largely the computational time. And so this is a fast implementation. And more on the real data set, we also apply our methodology on the trauma base, based on the measurements to predict the platelet level. After cross-validation, here we present the L2 norm of prediction error. And we see that our method AP slope is comparable to random forest. But in addition, we also have interpretable model selection and estimation results. So now in conclusion, we propose an AP slope which penalizes larger coefficients more stringently to control the false discovery rate. Meanwhile, it applies a weighting matrix to improve the estimation. And the modeling in Bayesian framework can give us much detailed structure about the predictors such as the sparsity and also the signal stress. Our simulation studying shows that AP slope is competitive to other methods in terms of power, FDR, and also the prediction error. For future research, we want to consider how to deal with categorical or mixed data and also deal with other missing mechanisms. Thank you very much for your attention.
Any questions? Have time for one. Please.
I think it sounds really cool, but I'm wondering why you cannot combine sort of like standard lasso or rich regression with multiple imputation.
Why that was using multiple imputation?
Yeah.
Yes, here I just used the mean imputation as a baseline method to compare. Indeed, we can also add multiple imputation inside.
Wouldn't that be a more fair comparison?
Sorry?
Wouldn't that be a more fair comparison?
More favorable? No.
More fair? So a more applicable solution?
Yes, but in fact, in our the objective is estimation and model selection. If we combine the multi-mutation and the other regression techniques, then we split the part into two terms, and then it will be difficult to obtain favorable results.